Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my 7th video in my series on algebraic number theory. And today I'm going to talk about the Euclidean algorithm. I have another video where I talk about the ordinary Euclidean algorithm for integers, which I think most of you are probably familiar with. It's kind of outlined on the slide, but as you'll see, we can apply the Euclidean algorithm not just to integers, it turns out, but to arbitrary Euclidean domains. As a matter of fact, that's why they got their name, Euclidean domain. So anyway, let's begin. So just to review, here's the Euclidean algorithm. This is for integers, but it's really the same algorithm for Gaussian integers or for any elements of any Euclidean domain. So just to review for integers, we suppose we want to find the GCD, the greatest common divisor of two integers, a and b. Well, what you do is you first find a quotient and remainder. You apply the division algorithm to a and b. So you find Q and R, the unique integers Q and R, such that A is BQ plus R, where R is strictly less than B. And then I'm assuming these are positive integers, by the way. And then you keep going. You go recursively. So now you just replace A with B and B with R. Sometimes we index these things. I guess we start indexing. They start doing it right after the first R. So we see B equals RQ plus Q1, we call the next quotient Q1 plus R1. And then again, R1 is going to be strictly less than R. By the same reasoning, we keep going recursively. Eventually, you get a remainder of 0. You have to get a remainder of 0 because these R's are all integers and each one's less than the previous one. And you can't have an infinite descending chain of positive integers. Eventually, you have to get to 0. So after a finite number of steps, we'll arrive at a remainder. Our last remainder, Rn, is going to be, I guess they call it Ri here. But we're going to get a final non-zero remainder, and that is going to be our GCD. So that's how this thing works. And there's even a thing called the extended Euclidean algorithm. We won't need it today, but you can even find, it turns out that, you can backtrack and you can keep track of the coefficient. So it turns out you can always write R, the GCD, as a linear combination of the two numbers you started with. You can write it as UA plus VB if you like, where U and V are integers. We don't have to do that here, but it's true. Anyway, that's the Euclidean algorithm for integers. But now I didn't even write it down for arbitrary elements of Euclidean domain. It's really the same thing. The only difference here is that instead of the inequalities on the right on the left side of the slide involve ordinary integers, you replace the norm. You replace the inequalities with inequalities on the norm. And it turns out that whenever you're dealing with a Euclidean domain, the norm. Remember, I told you the division algorithm. You can generalize that to Euclidean domains. So instead of having 0 less than or equal to R less than B, we have 0 less than or equal to norm of R less than norm of B. So the norms keep decreasing. And remember, the norm of Gaussian integers are also non-negative integers. So eventually they go to 0 by the same argument. So when you're done, when you finally find the GCD, you're left with something with minimum norm that is a common divisor of both things you started with. It also turns out that the norm is a common divisor of the norm of A and the norm of B. I won't prove that today, but that will be a useful result that we'll use later. Anyway, so I think I'm just going to finish up. This is going to be kind of a short video today. I'm just going to give you an example involving Gaussian integers. So suppose we're starting with the Gaussian integers alpha equals 8 minus I and beta equals 3 plus 4i. We want to find the GCD of these Gaussian integers. Well, we apply the Euclidean algorithm, which is the repeated division algorithm. So the first thing we do, I'm setting rho naught equal to alpha and rho 1 equal to beta. And then remember, division algorithm says that rho 2, I want to find the quotient remainder. I'm calling the quotient Q mu 1 and the remainder rho 2. So remember, we're going to get rho 2 equals mu1 times rho 1 plus rho 0. And to get mu1, we take the nearest Gaussian integer to the quotient rho 0 over rho 1, or if you like alpha over beta. And that's just 8 minus I over 3 plus 4i. When you do the arithmetic, you get the thing inside the brackets. The exact quotient is 0.8 minus 1.4i. You round that to the nearest Gaussian integer, which you can do just by rounding the real and imaginary components, and you get 1 minus I. So that's our first quotient. And now we calculate the next remainder, rho 2. We just say rho 2 is equal to rho 0 minus mu1 rho 1. We do all the calculations. I'm not going to go through it in detail here, but when you're done, you find that the result is equal to 1 minus 2i. Well, we're not quite done yet. Remember, we have to keep going till we get a remainder of 0. So let's just do one more step. So let's calculate the next quotient, the nearest integer to rho 1 over rho 2. If you do that calculation, you find you get actually an exact Gaussian integer. You get minus 1 plus 2y in brackets. And since it's equal to the thing in brackets, that means there's no remainder. We didn't even really have to compute the next remainder because we already got a quotient that was an exact Gaussian integer. That means our previous remainder was the GCD, and that was minus 1 plus 2y. So that means that our GCD is minus 1 plus 2y. Of course, the GCD is only unique up to a unit. It turns out you could also write this as 2 plus I if you want, just by multiplying the whole thing by minus I. But anyway, this is good enough. And to see that this is a GCD, this is a common divisor, both alpha and beta, we can divide both of them by minus 1 plus 2i. If we do that, we see that 8 minus I, that was our alpha, that's equal to minus 1 plus 2i times minus 2 minus 3i, and 3 plus 4i, that was our beta, that's minus 1 plus 2i times 1 minus 2i. Just that 1 minus 2i is really just a that's just a conjugate of minus 1 plus 2i. So it's a unit times a square of 1 minus 2i, it turns out. So anyway, that completes my video for tonight on the Euclidean algorithm actually, I'm not quite done. You might want to know why we care about all this. And, what we're doing right now is pretty abstract. And this is usually the case. I mean, this is kind of the idea of algebraic number theory. I want you guys to get used to what's going on here. We're dealing with an algebraic number field. We're dealing with, in this case, the Gaussian integers, the ring of Gaussian integers, which is an extension of the ordinary integers. But we care about them because it turns out when we pull back, so this is called lifting. Remember how algebraic number theory was motivated by trying to solve certain types of Diophantine equations. Well, it turns out that the machinery that we're using right now will actually help us solve some otherwise be very difficult um, uh, problems involving ordinary integers. Namely, we'll be able to actually kind of kill two birds with one stone with what we're doing right now. Because it turns out that the Gaussian integers are very closely related to the sums of two squares. Remember that the norm of a Gaussian integer, the norm of a plus bi is just a squared plus b squared. So that fact is going to shed a lot of light on what types of integers we can represent as the sum of two squares and exactly what those representations are. So we'll be able to solve two problems ultimately, two otherwise very difficult problems. One of those problems is, I think I mentioned this in my first lecture on algebraic number theory, the Diophantine equation involving representing arbitrary positive integers as a sum of two squares, figuring out how many ways you can do that and what those ways are. We'll be able to do that. And I think we'll be able to do that after a few more lessons. And another thing we'll be able to do is we'll be able to characterize all Pythagorean triples, ABC. As a matter of fact, we'll be able to find all triples of positive integers a, b, c, such as a squared plus b squared equals c squared, such as 3, 4, 5, 5, 12, 13, 8, 15, 17. Those are some simple examples of primitive ones. But not just primitive ones, but, ones that are multiples of those, like 5, 10, or 15, 20, 25, things like that. 9, 12, 15. You can multiply a primitive one by any arbitrary integer. That's not that exciting. But anyway, we'll be able to do both of those problems pretty soon. So that's a big reason why we care about what we're doing right now. So anyway, that concludes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.